So you're back for another AI deep dive with us. This time, we're tackling how those massive large language models are trained. You know, those LLMs with trillions of parameters. It's like, imagine trying to organize this giant library with trillions of books, each word being a parameter.
Yeah, it's mind-boggling.
It takes serious horsepower, multiple accelerators all needing to talk to each other, and at super high speeds, too.
And that's where it gets tricky. And expensive, honestly. You need high-speed interconnects like InfiniBand, and that's not easy to come by.
Exactly. Not accessible for everyone. But imagine if there was a way to train these massive models with less communication, between those accelerators.
Yeah.
That's where this research paper on DeMo comes in. DeMo, Decoupled Momentum Optimization. It's causing quite a buzz.
It really is. The whole AI world is talking about it.
Yeah.
Because it challenges like fundamental stuff about how we train these models.
Okay, so let's break it down. The issue is, training these huge models usually means tons of data transfer. Between accelerators, I mean. It's like sending a whole encyclopedia every time you update one definition.
Yeah, and those high-speed interconnects become a major bottleneck. They limit how fast you can train, how big you can go with these models.
And there are existing solutions, right, trying to reduce that data transfer. Things like compressing the data or using some complex math tricks.
Right, but they often come with their own problems. It's like trying to fit a giant puzzle into a tiny box, you know? You can force it, but you might lose pieces or damage them in the process.
So some lose crucial information, others become too expensive computationally.
Especially with these massive models we're talking about.
So DeMo comes in with this radical new idea. Instead of squeezing all that information through the bottleneck, it decouples things. It's like each worker in a factory has a bit more freedom to work independently, and then they combine the results later.
Right. It allows for what we call controlled divergence, meaning the optimizers on different accelerators, they're allowed to, like,
Yep.
explore slightly different paths to reach the optimal model settings.
That's interesting. Now, this approach, it hinges on three conjectures. The researchers haven't formally proven them, but they've seen enough evidence to suggest something big is happening. What's that first conjecture?
So the first one is that the fast-changing components of the model's momentum, think of it like the model's short-term memory. They have these similar patterns across different parts of the model.
Okay, so instead of sharing every tiny change, you can just send the essential information, like sending a summary instead of the whole book.
Exactly. That's a great way to put it.
Makes sense.
Yeah, totally.
What about the second conjecture?
Okay, so the second one says those fast-changing components, they need to be applied right away. While the slower-changing components, like the model's long-term memory, those benefit from being averaged over time.
So it's like filtering out the noise, right? Focusing on the overall direction of the learning.
Yeah, you got it.
And the third one, what's that about?
The third conjecture, it says that even though they change slowly, these slow-changing components, they're super important for the long-term learning. They're like the foundation of a house, essential for stability.
So DeMo makes sure these are preserved, the model doesn't lose its bearings. Gotcha. So we have these three really intriguing conjectures. But how does DeMo actually put them into action? How does the algorithm work?
Okay, picture this. DeMo is like a filter, separating the high-frequency components, the rapidly changing ones, from the low-frequency components, the slow and steady ones. But instead of using complex calculations, it uses a clever trick. It's called the discrete cosine transform, DCT for short.
DCT. That sounds a bit complicated.
It might sound intimidating, but think of it like this. The DCT is a way to break down a complex signal, like a piece of music, into simpler parts. And it's very efficient, already built into most modern GPUs.
So they're leveraging existing technology. Okay, but how does the DCT help with this decoupling and reducing the communication?
That's the really clever part. DeMo uses the DCT to identify and extract only the most important information, those fast components we talked about. And then it synchronizes just those between the accelerators. Like instead of sending a whole truckload of packages, you just send a postcard with the key points.
And that leads to a massive reduction in the amount of data being transferred, right?
Exactly. We're talking going from gigabytes of data down to mere megabytes.
Wow, that's a huge difference. This is fascinating. It seems like this could really revolutionize how we train these massive AI models. But before we get ahead of ourselves, can we dive a little deeper into exactly how DeMo uses the DCT? It feels like that's the core of how it achieves this efficiency.
Absolutely. It's worth unpacking that a bit more. Remember those conjectures we talked about? The one about the fast-moving components having similar patterns across the model?
Yeah, I remember.
Well, the DCT helps DeMo exploit that.
Okay, so walk me through this.
Mm-hmm.
How does identifying those patterns translate to less data transfer?
So the fast-changing components, the ones we want to prioritize, they typically have high frequencies in the signal. And the DCT, it acts like a sieve, separating those high-frequency components from the rest.
So instead of transmitting all the data, DeMo focuses on those high-frequency components identified by the DCT. And because those have similar patterns across the model, you don't need to send as much.
Exactly. It's like having a shorthand code. You send the code instead of the whole message, and the receiver can reconstruct the full message knowing the pattern.
That's brilliant. This DCT trick, it's the heart of DeMo's ability to reduce communication so drastically. Okay, so we understand how it works. But what are the results? What happened when they put DeMo to the test?
Well, they tested it out, training these big LLMs using a framework called Olmo and a massive data set called DOLMA.
Dolma got it.
But what they found was pretty amazing. DeMo, it not only matched, but in some cases it actually exceeded the performance of Adam W.
Adam W.
Yeah, it's considered like the gold standard optimizer for these models.
Hold on. So it's not just about reducing communication. It's about maintaining or even improving the quality of the model.
Exactly.
Wow.
And they did all this with drastically less communication. Like in some cases, they reduced data transfer by a factor of over 1,000.
1,000. That's like sending a postcard instead of a whole truckload and still getting everything across perfectly.
That's the idea.
So what does that kind of efficiency mean for AI development?
Well, imagine this. Researchers, maybe in developing countries or small startups, they can now train these cutting-edge models without needing the most expensive hardware.
That would be a game changer, wouldn't it?
It would. It could level the playing field in a way we haven't seen before.
More people contributing to AI. That's fantastic.
And think about the cost savings, too. Those high-speed interconnects, they're not cheap. If DeMo allows us to use more common hardware, the cost of entry goes way down.
Right. Okay, but let's not get too carried away. DeMo is still pretty new, right?
It is.
And those three conjectures, they still need to be formally proven.
True, there's more research to be done. But the initial results are very encouraging. And the fact that they released an open source implementation, that's a great sign.
It means more people can experiment with it, refine it, push the boundaries even further. This feels like the start of something big.
It does, it really does. And what excites me is that DeMo isn't just about incremental improvements. It's about fundamentally changing how we think about training these AIs.
Now, you mentioned a specific variation of DeMo called the Signum variant. What's that about?
Right, the Signum variant. It's even more memory efficient. It simplifies how those fast components are identified and extracted.
So a shortcut through the algorithm.
Yeah, think of it that way.
And that reduces the memory footprint even further.
Exactly.
So even more lightweight, even more efficient. Perfect for those with limited resources. Did they see any performance difference with this Signum variant?
You know what? They found it performed just as well as the standard DeMo, in their tests at least. And it used less memory.
Wow, so it's a very promising option then, especially for those working with limited resources like we were talking about. Yeah. Okay, so we've talked about the benefits. Are there any downsides or challenges that we should be aware of? It seems almost too good to be true.
Well, one challenge is that it requires a slightly different approach to optimization. Traditionally, we've focused on keeping all those accelerators perfectly in sync, but DeMo introduces controlled divergence, remember?
Right.
So that might take some getting used to for developers.
That's like learning a new dance, I guess.
Yeah, exactly. And another open question is generalizability. So far, they've mostly tested it on language models.
Right.
We still need to see how well it performs on other types of models, like computer vision models or those used for reinforcement learning.
So more research needed to see how widely applicable it really is. But even if it's most effective for certain types of models, it's still a huge step forward, isn't it?
Oh, absolutely. And it could inspire similar approaches for other types of models. DeMo has really opened up a whole new avenue for exploration in AI training.
And speaking of exploration, let's revisit those three conjectures that are at the heart of this approach. Can you remind us what they are and why they're so crucial?
Sure. The first one, it's about spatial autocorrelation. Basically, it means the fast-changing components of the model. They tend to have similar patterns across different parts of the model.
Not just random changes happening everywhere there.
Right, there's structure to it. And that's what allows DeMo to only communicate the essential stuff.
Instead of every little detail?
The second conjecture, it states that these fast-changing components, they need to be applied right away, but the slower-changing ones, they benefit from being averaged over time.
Like separating urgent messages from the routine updates?
Exactly. That's a great way to think about it.
You act on the urgent ones immediately, but the routine ones can wait.
And then the third conjecture, it's maybe the most surprising one, it says that those slow-changing components, even though they might seem less important, they're actually crucial for the long-term learning.
Like the foundation of a house, you said earlier.
Exactly. Essential, but not flashy.
So these three conjectures, they explain why DeMo's approach works.
Yeah, they provide the theoretical framework for the whole algorithm.
Okay, now, we talked about the discrete cosine transform, the DCT, and how DeMo uses it. Can you walk us through exactly how that works?
Sure, think of the DCT as a way to transform a complex signal into a different representation, one where the fast-changing and slow-changing components are easier to separate.
So not changing the information itself, just changing how it's represented
Right,
to
exactly.
make it easier to work with.
Now, the DCT is really good at separating signals based on their frequency. Frequency meaning how quickly a signal changes over time.
High frequency changes quickly, like a stock ticker. Low frequency changes slowly, like the tides.
You got it. And the DCT can take a complex signal and break it down into a sum of simpler signals, each with a different frequency.
Like taking a smoothie and separating it back into its ingredients.
Perfect analogy. And the reason the DCT is so efficient is because it's a well-understood tool. It's been used in all sorts of applications. Image compression, audio processing, you name it.
So they didn't have to reinvent the wheel here.
Nope, they leveraged existing knowledge.
Which is one of the reasons DeMo is so promising, right?
It is. It's built on a solid foundation.
Okay, so we have this DCT. It can separate signals based on frequency. But how does that actually help DeMo reduce the communication overhead?
Remember that conjecture about spatial autocorrelation, where the fast-moving components have similar patterns across the model?
Yeah, I remember.
Well, the DCT helps us identify those essential patterns by separating the signal into its different frequency components. The fast-moving ones, they tend to have high frequencies. The slow-moving ones, low frequencies.
So DeMo uses the DCT to zero in on those high-frequency components.
Precisely.
And because of those similar patterns, it doesn't need to send the whole signal,
Just those key components.
like sending a telegram instead of a whole novel.
Exactly. You get the message across without all the extra words.
So that's the key to DeMo's efficiency. It reduces the amount of data that needs to be sent, which reduces the need for those expensive high-speed connections.
That's it.
It's amazing how a mathematical trick can have such a big impact.
It is, and it shows how innovation can come from unexpected places.
It pays to be curious, to explore different fields.
Absolutely. That's how breakthroughs happen.
Okay, so we've covered the DCT in detail. What else is there to explore in this deep dive?
Well, I think it's worth looking at the actual results from the experiments. They tested DeMo on training language models using the DOMA dataset, remember?
And they found it performed just as well or even better than Adam W, and with much less communication.
Right, but let's look at the specific numbers.
Okay, I love getting into the nitty-gritty.
So let's start with the training loss. It measures how well the model is learning. Lower loss means better learning.
And they found DeMo's loss was very similar to Adam W's, even with significantly less communication.
Yes, for example, in one experiment, they used a 1 billion parameter model. DeMo had a final training loss of 2.63. Adam W had 2.73. And that was with DeMo using less than 5% of the communication bandwidth.
Wow, that's a huge difference.
It is.
It means DeMo can achieve the same level of learning with a fraction of the communication.
And they also measured how well the models performed on some standard benchmarks, things like HelloSwag, ARC Easy, and PQA.
And how did DeMo do?
It performed similarly, or even slightly better than Adam W, for example on HelloSwag, which tests common sense reasoning. DeMo got 48% accuracy, while Adam W got 43%.
So not only is it more efficient, but it might even lead to better performance.
That's what the results suggest, and these results were consistent across different model sizes and settings.
So it wasn't just a fluke.
No, it seems to be a real robust phenomenon.
So DeMo is more than just a cool trick.
It is.
It has real-world implications.
Definitely. And those implications could be huge. If DeMo makes large-scale AI training more accessible, it could change research, innovation, how we live and work.
It's exciting to think about.
It is, and it reminds us that we're still in the early stages of AI. There's so much more to learn.
So where do we go from here? What's the next chapter for DeMo?
Well, one thing is to explore the theory behind it more. Those conjectures, they still need to be rigorously tested and proven.
We need to solidify the foundation.
Exactly. And another thing is to test DeMo on a wider range of AI models and tasks. We've mostly seen it with language models so far,
Right.
but it could be applied to other types like computer vision or reinforcement learning.
It's like seeing how far a new tool can go.
That's a good way to put it.
They start with one application, but then you realize it can do so much more.
And that's the beauty of innovation. It leads to unexpected connections and possibilities.
So the future of DeMo is looking bright,
It is.
and it'll be interesting to see how it evolves and impacts the field.
Definitely.
But before we wrap up, there's one thing I want to touch on.
Oh, what's that?
We talked about how DeMo uses the DCT to find and extract those high-frequency components. But I think we should explain what the DCT is and why it's a good fit for this.
Yeah, you're right. It's easy to get lost in the jargon, but understanding the DCT is key to appreciating how elegant DeMo's approach is.
So break it down for us. What is the DCT and what makes it special?
Okay, basically, the DCT is a way to transform a signal, like a sequence of numbers, into a different representation, like translating a sentence from one language to another.
So you're still saying the same thing, just using different words.
Exactly.
And in this case, the new language makes it easier to separate those fast and slow changing components.
Precisely. Now, the DCT is especially good at separating signals based on their frequency, how quickly they change over time, remember?
High frequency changes quickly like hummingbirds' wings. Low frequency changes slowly like the seasons.
Exactly. And the DCT can take a complex signal and decompose it into simpler signals, each with a different frequency.
Like separating a smoothie back into its ingredients.
Another great analogy. And the DCT is efficient because it's a well-studied mathematical tool.
So they're not starting from scratch,
Nope, they're building on what we already know.
which makes DeMo even more promising.
Absolutely.
Okay, so the DCT can separate signals based on frequency. But how does that help DeMo reduce communication?
Well, remember that conjecture about spatial autocorrelation, where the fast-moving components have similar patterns?
Yeah.
Well, the DCT helps us find those patterns by separating the signal into its different frequency parts.
Fast-moving ones have high frequencies. The slow-moving ones have low frequencies.
Right.
So DeMo uses the DCT to focus on those high-frequency components
It contains
and the most important information.
And because of those similar patterns, it doesn't need to transmit everything.
Just like those key high-frequency parts.
Like sending a telegram instead of a novel. You get the essential message across without wasting bandwidth.
That's how DeMo is so efficient.
It reduces the amount of data being sent, which means less reliance on those expensive high-speed interconnects.
A clever trick with a big impact.
It is, and it shows how innovation can come from anywhere.
We need to be curious and open-minded.
Absolutely. That's how breakthroughs happen.
Okay, so we've covered the DCT thoroughly. What else is there to explore in this deep dive?
Well, I think it's worth thinking about the bigger picture here. DeMo came about because we need to train these increasingly large AI models.
Right, those models are getting bigger and more complex all the time.
Exactly. They need more computing power, faster communication, and that's creating a bottleneck.
It's limiting who can participate in AI research, what kind of research can be done.
It is. It's like trying to build a skyscraper with only hand tools.
Okay, I can see that.
You might lay a few bricks, but you'll never reach the top.
And DeMo is like inventing the crane.
Exactly. It's a new tool that lets us build bigger and better.
And it does that by challenging how we think about training AI. Instead of forcing everything through the bottleneck, DeMo finds a way around it.
It's a whole new way of thinking, more aligned with the real world.
It's like limitations can actually breed creativity.
Absolutely. When you have to work within constraints, you find clever solutions.
So DeMo is more than just a technical innovation. It's a philosophical one, too.
It shows the power of problem solving and challenging assumptions.
And it's a sign that AI is constantly pushing boundaries. So where do we go from here? What's next for DeMo?
Well, we need to keep exploring the theory behind it. Test those conjectures, make sure they hold up.
Make sure the foundation is strong.
Exactly. And we need to test DeMo on more types of AI models and tasks, not just language models.
Right, see how far it can stretch.
Exactly.
That's the exciting part of innovation.
It is. You never know what you might discover.
So DeMo's future is full of potential.
It is. I'm excited to see where it goes.
Me too, and I'm sure our listeners are as well.
I hope this deep dive has given them a good understanding of it all.
I think it has. We've covered a lot.
From the technical details to the big picture.
And we've tried to make it accessible and engaging.
I think we've done a good job.
All right, so let's wrap things up.
Sounds good.
Any final thoughts?
Just that demo shows us that innovation can come from anywhere. It's about being curious, creative, and working together.
And it shows that the future of AI is full of promise.
Absolutely.
All right, let's end our deep dive into DeMo here. Thanks for joining us.
It was my pleasure.
We've explored a lot in this deep dive. The problem of those communication bottlenecks, DeMo's solution, how it uses that DCT trick, all to get those amazing results. But we want to leave you with something to think about, something that goes beyond what we've discussed.
You know, DeMo was designed for those huge language models. But what about smaller AI models, the more specialized ones?
The kind that need to run on devices with limited resources.
Yeah.
Right? Like smartphones, wearables,
Exactly.
maybe even tiny sensors embedded in, like, everyday objects. Could DeMo's principles work there? That idea of decoupling, selective synchronization.
It's an interesting thought. Imagine powerful AI models that are also lightweight and adaptable. AI that's not just in data centers, but in the devices we use.
That's a powerful idea. What if your smartphone could personalize its own AI assistant, learning from you without sending all your data to the cloud?
Or a network of tiny sensors, analyzing environmental data in real time, adapting on the fly.
Without needing a central hub.
It could change everything.
It could. It's exciting and a little bit scary at the same time.
Definitely worth exploring.
It makes you realize we're just scratching the surface of AI's potential.
We are. There's so much more to discover.
So to our listeners, as you dive deeper into AI, keep this question in mind. Could DeMo's principles be the key to a new generation of AI? Lightweight, adaptable, transforming not just the cloud, but how we live and interact with the world.
It's a question worth thinking about. Maybe you'll be the one to find the answer.
Thanks for joining us on this deep dive into DeMo. Until next time, keep learning, keep questioning, and keep exploring the amazing world of AI.